degrees of freedom to solve any problem entirely on its own. Now, when we're solving a motion planning problem, so this is to evaluate now the intermediate design, we use a sparse regularizer that is saying, use the degrees of freedom of the virtual end effector as little as possible. Right? So if there's some part of the motion that the intermediate design can accomplish by itself, then no degrees of freedom in the virtual end effector should be used. And if there are deficiencies in the intermediate design, then the virtual end effector has to come in and do some of the work that could not otherwise be done. So this example now shows the process of searching for solutions. So we have an initial robot design here. We're not visualizing the end effector, but what we're seeing is now the motion planning problem that is solved for this hybrid design that includes the virtual end effector. And basically, after evaluating a very small number of possible designs, it figures out that this robot has enough degrees of freedom to solve the desired trajectory for the end effector. Now, this is a very simple example, and of course, we can make it arbitrarily more complex. In this case, we said, okay, let's also give it a relatively complicated environment that the robot arm has to operate in. So this might be useful for an inspection task in some kind of crowded environment. And this is the robot arm that was designed automatically, so being able to follow the trajectory of the end effector while avoiding the collisions with the environment. And here's another example that's now going towards legged robots. So in this case, what we have is a specification of the motion of the center of mass of the robot, as well as trajectories for the end effector relative to this, to the motion of the center of mass. And this is a design that gets created automatically, and it gives rise to some pretty interesting mode of locomotion. And then this is the physical prototype that we created based on the design that was computed automatically. So with this project, we started to investigate the challenge of figuring out discrete aspects of the design, so how many actuators are needed, and roughly speaking, how they should be connected relative to each other. But of course, there's also a very important aspect of the design that has to do with continuous parameters. And for that, we can just go back to this picture that we saw a bit earlier. There are parameters that are given by the user, which are denoted by these red arrows, and these define the design, the kinematic design of the robot. So it might specify, for example, the width and height of the body, or the lengths of all the individual links in the robot design. And basically, all of these parameters, we're just going to call them P, and they are initially just provided by the user. And as we're solving for an optimal motion using trajectory optimization, really the set of design parameters is implicitly added to this optimization problem. So what this means is that if you were giving us a different robot design, so a different set of parameters that define the kinematic proportions of the robot, well, the motion would also have to look different to account for this new design. So one question that we were trying to ask is, if we have a notion of an optimal task that we're trying to achieve, can we automatically figure out what the good set of design parameters P looks like for this task? And just to come up with a mathematical formulation for this, the observation is the following. If we're looking at the gradient of this energy that we're minimizing for during the trajectory optimization process, as an optimal solution, it will be zero, right? Because we try to get to a local minimum of it. And this condition is true for any set of parameters that are given as input, right? So for any set of parameters P, if we solve the trajectory optimization problem until we find the local minimum, then the gradient of this objective that we're minimizing with respect to M will be zero. Now, if I give you a function that is constant, so the fact that it's zero doesn't matter so much, but the fact that it's constant is very important. Well, what this means is that the total gradient of this function with respect to the set of parameters that it's invariant to has to be equal to zero. Now, if you expand this using the chain rule, you end up with this expression. And if you rearrange it, you end up having this. So let me just explain what this means. This DMDP, this Jacobian, tells us how the optimal trajectory, the optimal motion for a particular robot changes with respect to the design parameters. So if you were to wiggle the design parameters a little bit, this would tell you to first order how you should change the motion such that it remains optimal. And the thing that's important here is that this expression that we have, basically the partial derivative of the gradient of the energy with respect to m and p, these terms can be computed analytically. And this is very important because the relationship that we had earlier, which is m of p, the first line here, does not have a closed form solution. Right? So even though we have this pretty complicated expression that we have to solve numerically, this Jacobian we can compute analytically. So that's quite important. And so now that we know how to compute this Jacobian, well, we can start using for design tasks. And here are a few examples. So this is a robot that we designed a little while back. And we loaded it up with as much weight as we could until we got to the limit of what the actuators could do. Right? So basically with this, the robot can still walk forward, but just barely. We're at the limit of this. And now, this is a very simple way of using the Jacobian that I was describing earlier. If we want to change some aspect of the motion, so we're saying, for example, we want the actuation forces to decrease, to get lower, then we can come up with a corresponding change to the design parameters through the pseudo-inverse of the Jacobian that will make it so. So this then tells us how to update the design, and we can recompute an optimal motion rate, and so on and so forth. So with this now, we can see how this design changes automatically to decrease the actuation forces. And basically, if we look at the forces required to carry this payload before and after the design optimization, we see roughly 30% improvement. And once you look at this design, you would say, okay, the changes make sense. It makes sense that you would try to walk with straighter legs to minimize the moment due to the payload. So it's kind of a proof of concept that it's doing something quite reasonable. And of course, we can start applying the same kind of technique to robots that are more complicated, have a much larger design space. So here's an example of a virtual design of a robot that uses a series of linear actuators. So these could be, for example, related to hydraulic actuators that we've seen before. And again, we can now ask, how should the design and placement of these actuators change to start minimizing the actuation forces that are required? And now, this is the example between the initial design that we started with and the optimized design that, again, was generated automatically. And it achieves a reduction in the actuation forces of about 50%. So it's quite noticeable in terms of the performance of the system. Now, where can we go with this? Well, I think that there is a drive to see robots having increasing complexity. So I really like this conceptual design of the Nadia robot that IHMC is planning to work on. Very, very complicated design, a lot of different parts, probably a very large repertoire of motions that we want this kind of robot to perform. And at some point, the complexity of the design just gets too difficult for traditional engineering approaches where you just try different parameters, build a new robot, see if it goes better than the one before. So I would hope that that's where computation will start to play a big role. And also, if we look sort of many years into the future, I think many of us have the goal of creating robots that start to approach the performance of biomechanical systems. In biomechanical systems, compliance in the mechanics is a very important part. And again, that's the type of problem domain where we're going to see so many parameter spaces that are so high dimensional and also very difficult to reason about without dedicated computational tools. This, I'd like to end the talk and happy to take a few questions. Yes, definitely. So the vision that I have is that at some point hardware and software will really work very nicely together. And if we have reconfigurable hardware, and that just gives us new dimensions in the design space, then in principle these types of techniques will be able to leverage that capability. I would say we're definitely not there right now, but I don't really see a reason why in 5 to 10 years computational resources and algorithms will both get better, so that, yeah, that's definitely within reach.
Once you have it designed, how much effort is put in to actually make the physical robot? Like, is it just really simple, or does it take a lot of extra effort?
Well, that really depends a lot on the robot. So for the prototype we built for the mobile robots with wheels and legs, it took us, with the fabrication techniques that we're using, about a week. But much of that was just the time required to 3D print the parts. So if that technology improves, or if we have what I envision as the ideal modular robotics kit, then the fabrication will be much faster. Well, so it's definitely a non-convex space that we have to be exploring, and that's just the reality of the world that we live in. So the best we can do is hope for a good local minimum. For all these problems, the initial guess that you're starting from matters a lot. And so we do work on basically the numerical side, so how do we get these optimization formulations to be as robust and fast as possible. But we're also doing work on worm starting to make sure that we do start from a reasonable initial guess.